method class, I thought that this topic will fit quite well together with the course. So I will focus on talking about some problems about embedding cycles and trees in some graphs with pseudo-random properties. So just very quickly, maybe remind ourselves what is GMP. Okay, so okay, Erdős-Rényi binomial random graph. So it started from their work from 1959, actually. As a formal definition, we write GMP is actually a probability space such that when you draw a graph according to this space, then the vertex set is, I will use bracket n to indicate the first n integers, let's say on n vertices, we fix n vertices, and the edges, every pair is added with probability p, okay? I'll use this notation to mean the pairs in n, in bracket n. Independent of others, okay? So it's very important that we have this independence here. Since introducing in the 50s, there's been lots of studies about various aspects of random graphs. So today, the first method we want to cover is the depth first search, a very basic algorithm. It turns out to be very powerful and can give some very short and elegant path to find the graph that we want. And so before introducing it, so let me motivate you by the question that we concern today. So today, the question is, okay, we're given the GMP, how long is a path question? Okay, this is the question. So what does it mean? What is GNC over n? Suppose C is a large constant. Then this graph almost surely has linear in n number of edges, right? The number of edges. Is concentrated like some constant times n. So when we have linearly many edges in a random graph, the question is how long a path can be asked. So there's a story here. I think back in 70s, Erdős was asking, when we have linearly many edges, then can you see a path of length linear in n? Then at that time, Semerity think otherwise. It's not possible. You can only have sublinear length path. So today we will see a very short proof showing that he was wrong. You can find indeed a linear in n path. So, right. Let's get to the first method that we want to cover. Is the depth. Depth research. Okay. This is a well-known algorithm. Let me just quickly recall. I would like to keep two pictures in mind when we talk about DFS. Okay, the first picture which is the searching picture, we keep this a picture of the tree in mind. So what do I mean? Let me give maybe better two pictures in mind. Okay, the first one is I will show by example. Suppose we have our graph G. Maybe let me use, G. I just draw some whatever graph, okay? Maybe like that. Okay, not too big, this one. Now I want to show you, quickly recall the DFS search on it. So the DFS search, you start with the arbitrary vertex, let's say this vertex, okay? So this is the first vertex that we visited. Then you look at if this vertex has an unvisited neighbor. If yes, we go there, okay? So for example, it has two neighbors, these two, right? Then we break the tie arbitrarily. If you have two unvisited, you go there. So say this is the second one. Then you continue this process, right? Okay, after two, you have three, 1, 2, 3, these three to visit. Let me just pick arbitrarily. Let's say we have this one, unvisited. Like we go like this. Then we can go like here to the fourth one. Okay, so this is not really a very good example. Let me delete this edge from the graph. Okay, then we keep going here. Let's say this is the fifth one. Now here comes the problem. We cannot go further anymore after the fifth step. Vertex number 5 that we visited has no unexplored, unvisited neighbors. So in this case, we're going to trace back. We're going to go back to the first vertex that has one unvisited neighbor. So we go back to 4. Again, all its neighbors visited. We go back to 3. Okay, 3 does have one, so we continue here. This is number 6. Okay. Now among all these 3, let's say I randomly choose this one. This is number 7. Again, we exhausted 7's neighbor, so we have to trace back to 6. So from this point on, it's very straightforward. We go, say, this way, 8 and 9. So the first picture I want to keep in mind is this tree structure. Okay, so let me draw it on the side. Six, 7, 8, 9. Okay, fairly simple. We've all seen this in undergraduate CS course. Right. So it turns out this very, very, very simple method can already solve the problem, the question that we want to study today. So let's get to it. But before that, I want to give you just quickly write down the precise procedure of the DFS, the second way of thinking DFS. So now let me write down the precise description. The second way I would like to think of is to keep track of 3 sets: the visited one, unvisited one, and the stack of current active vertices. Okay, so now let me write the formal algorithm. Let's say we have input is a graph G. Okay, then we initiate at the beginning. What we do is to pick an arbitrary vertex. Let's say arbitrary vertex V in G. This in this picture is this guy, right? We pick the first one. All right. After we pick the first one, so there's a reason that I try to make everything precise. So later on, it's easier for me to refer back to. So the 3 sets we're going to keep track of. The first one is S, which is the stack. Okay, we call it V1 .vs, where S is the length of the stack or depth of the stack. This is the searching stack, right? our starting point is S equal to 1, V1 equal to V. This is our initialization. The second set is U, the unexplored vertices. So at the beginning, apart from the first vertex V that we picked, everything else is unexplored. The third one is X, which is explored ones, okay? So just keep this letter X, U, and S in mind. We have the searching stack. So the second picture, it can be seen as something like this. We have our searching stack S, and on the left-hand side, we have our unexplored vertices that we want to explore. And whenever we explore vertices, we're going to push it to the stack, right? And then right-hand side is the vertices that we're done exploring. So this is the initialization. So let's write down the algorithm. We have two stages. The first stage, exploration stage. Okay. Exploration stage is saying if the last vertex, remember, this is the picture we want to keep in mind. The stack has the property that first in, last out, right? So we have this V2, V1. This is our stack. And here's unexplored vertices, explored vertices. Now we're saying that, okay, look at the neighborhood of a vertex, the last vertex on the stack, in the stack. Does it have a neighbor in U? Okay. If it does, let's say this guy. If it does, we're going to add one such neighbor to it. Let's call it U, okay? Let's call this guy little u to the stack, to S, okay? We will update the stack by inserting one more vertex. So this is the U will become on top of S, and S will be updated, the stack get elongated. We update also the length, little s to s plus 1 of the stack, the depth. And explore the set of explored vertices, we have explored U, so we're going to kick it out of the unexplored vertices, sorry. Then whenever we can do this step, we're going to repeat whenever we can. Okay. Now, when we cannot, here comes the case when we do not have a neighbor. Okay, this edge do not exist, the red edge. In this case, we're going to pop. We use another picture. So if there's no edge, then we're going to pop the top vertex to X, to the explored vertices. So the top vertex, we don't need it anymore. We can update X. Okay. And we will update the stack also. Now, since we pop the top one out, it becomes shorter. And the depth also become one shorter. Okay. So when we do this, the third one is whenever the stack is now empty, whenever this stack is now empty, we're going to repeat stage one, the exploration from the very beginning, and keep doing this. Okay. Otherwise, go to stage two. Stage 2, new components. So actually, whenever the step becomes empty, that means we finish the current component. So when step becomes empty, we look at the set of unexplored vertices U, and we ask if U is non-empty or not. If it's not empty, that means there's still a graph left. Then we will push some arbitrary vertex W in U to the stack. Okay. So now S is empty. We look U is still not empty. We push arbitrary vertex in. Then we update. So W becomes the first vertex in V in the stack, and S like that. Our depth of the stack come back to 1. We again update. Okay. Then we go to stage 1. We start exploration of the component containing W. Okay. The other possibility is we've exhausted all the vertices. So the unexplored vertices is empty. Then we terminate. So as you can see, I wrote this in a great detail just to make sure that we are on the same page of the notation and to keep these two pictures in mind. Now I'm going to list some very basic property that can be proven straightforwardly. And then using this basic property, we can give a short proof of the question that we raised at the beginning. Okay. First of all, note that DFS search on the graph G naturally yields a spanning forest, one tree for each component. Okay, with a natural ordering. So, so this is the picture here. You see, we have our first picture, we have our graph here, and after we do the search, we get this natural ordering on this blue spanning tree. By spanning, I mean a subgraph with vertex that visits all the vertices. Okay. Good. And also with a natural ordering such that the root of every subtree is the first vertex visited within the subtree. Okay, this is also a basic observation. What I mean is, let's come back here. Let's take a subtree. Let's say this one. As you can see, 6 is the first, the root of this subtree is 6. It has the smallest number label, meaning that it was visited the first among all the vertices in the subtree. This is also very basic. Similarly, let me list all these basic properties. I call it observation. Observation 3.1. Okay, the first observation is that the key observation that DFS is useful for finding a long path. The stack S always induces a path in G. right? Okay, let's recall. The vertices on this stack S, they always form path. Okay, because we basically go like a trail. We go, yeah, this is straightforward, I guess. We always, the next vertex to visit is always the neighbor of the current one. And whenever we have to trace back, then we pop out the current vertex. So this is the reason that it always induces a path. The second observation, which is also important, a trivial observation, is that every step we either push an unexplored vertex into the stack, we either do this red step, right? We push U into the stack S, or we pop the top vertex if it has no non-explored, no unvisited neighbors, then we're going to pop it out into X. So so that means the second one is each step observation, each step, we have two possibilities. Either the unvisited vertex decreases by 1, okay? Or X, the stack of explored vertices, increases by 1. And at the end, the explored vertices becomes the whole graph. Okay, I have a typo here. The next observation is that, also very important, no edge between U and X. So again, here's the picture. S always induces a path in the graph. The set of unexplored vertices and explored vertices, there's no edge. So S is a kind of like a cut set. There's no edge going like this. Okay. This will be also important. How to go back? Yeah. This, right. Okay. I hope this is clear. If not, I'll leave it as exercise to prove it yourself that there's no edge between U and X. The next, the very last one that we want to talk about, the observation, is that, right. So recall that for this every graph G, we can produce a forest F, a spanning forest. Here is the example, where every tree corresponds to a component. Since G here is connected, so here the F is just a tree, not a forest, not a, okay. So if we have an edge, for any edge, okay, for any G edge, let me just be clear, an edge in the graph, let's call UV. If it's not in the spanning forest, okay, a graph edge that's not in the spanning forest produced by the DFS, then one of them is a predecessor of the other in F. Okay, let me come back to this picture. What do I mean by that? So here, let's see. We have an edge. Let's say the edge 2, 8. I pick a random one. This edge is a graph edge, but it's not in the blue spanning forest produced by DFS, right? Now let's look at 2 and 8, the position. Then 2, this edge, this is our edge. 2 is a predecessor, ancestor of the vertex 8. So what I mean is that it cannot be the case that 2 is here. They belong to 2 different subtree. Okay, so in other words, if we have 2 different subtree, let's say this black one and this red one, then there's no edge between them. Okay, between 2 different subtree rooted at different one. Let's see, we have 4, 5 here, and 6, 7, 8, 9, right? There's no edge between them. So let me write this down. So I find it quite interesting that so far we're doing the most basic thing ever. We just like write down the algorithm and observe some very straightforward properties. Then suddenly it can give us some very deep results. So i.e., in other words, what this means is that there's no edge in G between subtrees with different roots. Or you can say that another way to say it, also important, we have a tree T, okay? You take a component, root it at R, a vertex R, okay? Then let's say T prime is a subtree of T rooted R prime. Now, if I let P to be the path from the root R prime to R in the tree T, then we must have the neighborhood, the G neighborhood of the vertex set of the subtree lies completely on the path. This is another consequence of the. Let me again go back to the picture to illustrate, okay? Oh, this picture is a little bit overwhelmed. Okay, let me draw another very simple example here, all right? Okay, looks a little bit artificial, but okay. Anyway, here's the DFS. Let's say we go like this, 1, 2, 3, 4. Now 4 has nothing, we go back. Then we pop here, 5, nothing. Then we have trace back to 2, 6, and 7. So the tree looks something like this. 1, 2, 3, 4. 3 has 2. This guy has 6. 6 go to 7. Okay, let's look at this statement. It says that let's take a tree. So this is our tree in F. Actually, in this particular case, they equal. We only have one component. Rooted at R. So this is our root R. Now you take a subtree. I take a subtree. Let's say this one. This is my subtree T prime. So here, 3 is my root, right? So 3 is R prime. So our path, P, this is our path P. This is our path P. Now look, the whole neighborhood of the subtree T prime, which is vertex at 3, 4, 5, all its neighbor lies on this path P, which is vertex 1, 2, 3. So this is our path P. It's true because the whole neighborhood of 3, 4, 5 is vertex 2. Okay? So we have all the basic properties down. Let's state the main theorem. Okay. So this following result is due to, I will give the proof given by Krivolovich, Lee, and Sudokov. He says that GNC over N, so when we take C sufficiently large, almost surely that means the probability tends to 1 as N goes to infinity, has a path not only linear in N, actually almost spanning path. Okay. This big O sub C notation means there exists some absolute constant. I think 10 will be okay, such that when capital C is sufficiently large, we get the path of length 1 minus 10 log C over C times N. Okay, so when C is sufficiently large, this is really error term, becomes sublinear in N.
Subscript C is different from the capital C, right?
Same C. That means the big O depends on capital C.
That's a bit weird. The constant depending on C times
Right.
C over C.
So that means there, okay, i.e. there exists the constant alpha. Actually, alpha equal to 10 is enough, I believe, such that and n, sorry, not n.
So
C
alpha does not depending on capital C, right?
No, does not. Right. Is this the absolute constant? Absolute constant.
Your notation is a bit confusing. The big O sub C, that C is constant C, not that's word constant, right? It's different from that.
So when we write big O of 1, we usually mean big O sub n of 1, right? That means there exists the absolute constant such that when n is sufficiently large, it holds.
Okay.
So now
okay, that's your definition of subscript there. Okay. Okay.
Right. Okay. Yeah, it's okay, maybe the notation needs some explanation here. So maybe let me just write it has length at least 1 minus say 100 log C over C times n. Okay, when for large C. Maybe 1000, you have to plug in some absolute constant, also sufficiently large. All right, once again, this basically shows that Semerdy was wrong, right? His intuition. So when we have linear GNC over N, how many edges it can have? Roughly Cn over 2, concentrated, highly concentrated around Cn over 2, which is linear in N number of edges. So it turns out that not just you can get the linear path, linear in length of the order of the graph, but also almost spanning here. All right, so let's see the proof of this result. Any questions about the statement? Okay, so the proof is very, very simple, short and nice. It consists of 2 steps. Let me first sketch you the step, and then we see a little bit, we see the detail. The 2 steps is first, we prove that we use DFS to show that if the graph is M-joined, which I will show you the definition, then we have a long path. Okay, this is the statement. Second step, then we use standard concentration to show that almost surely GNC over N is M-joined. Okay, then since by second step, the random graph, when we have linear number of edges, is almost surely M-joined, then by the first step, using DFS, since you're M-joined, you must have a long path. So let's see the definition of M-joined. This is very simple. That means when you have two disjoint set of size M, okay, then there must be an edge between them. So if you do a lot of extremal graph theory, then you can also say that the complement G bar is KMM free. Right? Another way to look at it. The complement of the graph does not have complete bipartite graph with M vertices on each side. Okay, so now we can complete the first step. Proposition 3.5. Okay, we have an M vertex graph G that is M joined. Then there exists the path of length at least more than M minus 2M. So if we can prove in the second step up here that almost surely the random graph GNC over N is M joined for some sublinear M, then we are done, right? And the proof of this is very simple. Well, very simple because we spent a lot of time elaborate the properties of the DFS here. So we're going to run DFS on G. So now the picture I would like you to have is the second picture, the three set that we have. The stack, which induce a path, the set of unexplored vertices on the left, and the set of explored vertices that we done exploring on the right. And recall, okay, so this is the picture I want to keep in mind. So we're going to run the DFS on G. At some point, recall that one of the observations is that the size of U is decreasing by one, at most one, at every single step. Either U go down by one or X increase by one. And U start with M minus one, all the whole graph except the initial vertex that we pick. So that means when U is dropping in size, X is growing in size, at some stage they have the same size. They don't change at the same simultaneously in a single step. At every step, either one stay put, U goes down by one, or U stay put, X go up by one. So at some stage, they become the same size. Let's call this guy X. Okay, little x. But then what does it mean? Do you recall that we do not have any edge between U and X? Another observation. Okay. And there's no edge between U and X. This implies that X is strictly less than M, right? Because our graph is M joined, we cannot have two disjoint sets of size M such that there's no edge between them. This is our assumption. So this implies that S, the stack size, is M minus 2X, which is bigger than M minus 2M. But then we are done because S induces a path, the other observation. This is the whole proof. Okay, very short, but very, very pretty proof. So all it's left to do now to show that GMP with P equal to constant over N contains the almost spanning path is to show that GMP the second step that I described above, is M joined for some small m. Then we can invoke proposition 3.4 and we are done. So this is quite standard. I will do it rather quick. Proposition 3.5, for large C, I do it for once and later on I'll leave it as exercise. We look at the random graph GNC over N. It is almost surely M joined for every M, at least turns out 3 is enough. Okay. Remember, this is the arrow term that we have in our theorem here. Log C over C times some constant, 3. Right. So the proof is a basic calculation. Okay, so you fix an M, then you take the union bound basically, union bound over all pairs of M sets not joined. Okay, you look at 2 M sets and estimate what's the probability that they not join, and we show that taking union bound it goes to 0. So we have N choose M square, meaning number of choices for this disjoint set A and B. Maybe you have to times N for the choices of M. And then let me just fix one N just to be simple for now, okay? Times 1 minus P, there's no edge between them. That means we cannot have all the edges, M square edges. Then you do some calculation. I'll list this calculation in the notes. So I will not cover. This is rather standard. It tends to 0 as N goes to infinity. Okay, this shows that the probability that you will ever see a pair of M sets not joined tends to 0. Then in other words, with probability tending to 1, all M sets, they are joined by an edge, at least one edge. Okay. So then the proof, if you combine proposition 3.4 and 3.5, we prove theorem 3.2. We get an almost spanning path in GNC over N. Okay, this is a very cute application, but the result is quite meaningful. So, so there's one more thing I want to talk about since we talk about DFS. Let's look at another application of DFS, of finding a pathing expander. Okay. Cycle. So expander is typically a graph in which, let me just draw a picture. It's typically a graph G such that if you look at its vertex set, its external neighborhood expands, not so small. Okay, so today we want to look at this linear expander, constant expansion. Definition. I call alpha K expander, where we have K, let's say K is an integer, which tell you the threshold of the sets up to size K, they expand, small set expansion. And alpha is some expansion factor, the positive real. Then we say that G satisfy that is a alpha K expander if for any X in vertex sets, not big, small set expansion, then we have its external neighborhood. This notation, external neighborhood is, we do not consider X itself, okay? It's at least expand by alpha portion, as in this picture, the constant expansion. Then the natural question is, in such expander, how long a cycle you can contain? So it turns out that, well, first of all, let's look at here. Maybe let me write it down more precisely. Question.
You have a
we
question
want
on the chatting?
Yes, okay. X is greater than K. No, X is at most K. This is different from, probably you are in the other lecture before. This is different expander, okay? That is sublinear expander will require sets to be large enough to have expansion. So this is constant expansion, and we only require all small set to have expansion. So for sets up to size K, we have expansion. So the question we cared about is how long a cycle we can find. In alpha K expander. Okay, well, definitely no longer than linear in alpha K. This is because what we can do is you can take a complete bipartite graph with alpha K vertices on one side and K vertices on the other side. So this is alpha K expander, yes, right? So for sets up to size K, look at the right-hand side, its external neighborhood is at least alpha K. And the longest cycle here, you bounce back and forth, is twice the size of the other side, so it's 2 alpha K. And turns out we can prove that we can find a lower bound within constant factor of this optimal bound. So theorem 3.7 is that we have K and alpha, okay, let's set it up. And we have G is an alpha K expander. Then there exists a cycle of length alpha K over 2, okay? So the reason I want to talk about this is that I want to demonstrate that not only DFS can give you long path, but also can give you long cycle. And later on, we will introduce another very important technique, the Pochas rotation extension and edge sprinkling, which can improve on the constant factor here. But for now, this is a very short proof of giving a very long cycle in expander. So basically, this theorem, let me see how much time I have left. Yeah, I have enough time. This theorem 3.7 follows very easily from the following results of Alon and Krivolovich. So their result itself is proof using DFS. Okay, so 3.7 follows immediately from this result, 3.8. It says that we take K and T, natural number, with T at least 2. Okay, and we have a graph G is connected graph. In fact, you can drop the connectedness here, but I'll show a shorter proof, just assume additionally. It's easier. So we have an n vertex graph connected on at least k vertices, or more than k vertices, satisfying that for n in W of size between k and k over 2, okay, in this interval of k over 2 to k, we must have its external neighborhood of size at least t. So this is slightly different from the alpha k expansion. There, I require all the sets up to size k to expand. Here, I just need expansion between k over 2 to k, such that the external neighborhood is at least t. Okay? Then, if we have this expansion, G has a cycle of length at least t plus 1. So quickly, why 3.8 implies 3.7? Simply, you take t to be alpha k over 2, right? The proof of, so I don't want to write it down. Let's see. Let's prove 3.7 using 3.8. By 3.7 hypothesis, we know that G is alpha k expander. That means every W between k and k over 2 size, its external neighborhood is at least k over 2 times alpha. Okay, so we can take t with k over alpha times k over 2. Then by the conclusion of 3.8, we get a long cycle, alpha k over 2. So the proof, let's see the proof of theorem 3.8. And we will conclude for today. So the proof is also very simple. Now, the proof, we're going to again run DFS, but I want to switch back to the first picture that we have. You see, previously, when we find almost spanning path, we made use of this picture of the stack and 2 sets, explore, unexplored. Now I want to switch back to the first picture, the forest picture. Okay. Now let's quickly recall the property. In this forest picture, between 2 different subtree, there's no edge. Okay? Rooted at different vertices. And the second property I will use is that the external neighborhood of a subtree T prime lies entirely on the path P leading from its root to the root of the whole tree, P. Okay? So that's given the formal proof. Right. Oh, for this proof, 3.8, I also need a simple result on trees. I will leave it as exercise. That whenever we have a rooted tree, T on at least k vertices, okay, then there exists a vertex V and the subset X, which is children of V in the tree T, such that if you take the union of subtrees rooted at X, this size has order. Okay, if I write has order, I don't need this size. Between k over 2 and k. So let me draw a picture. So when you have a tree T on at least k vertices happen to be binary, let me not make it binary, okay? Then I claim that you can find a vertex V and some subset of it. So let me make it more general. and subset of it, let's call X, such that if you take the union of the subtrees root here X, which is a subset of a single vertex, then the union of this blue blob is between K over 2 and K. I leave it as a simple exercise. Basically, you just go down along the root and try to see when you can find such a the vertex. So let's come back to the proof of theorem 3.8. Recall, 3.8 says, whenever for sets between size K over 2 and K, its external neighborhood is T at least, then we have a long cycle. So, let T be the tree from DFS run on G. Okay, so we have our a tree. You run a DFS, you get this tree, and we let V and X be the vertex and its subset of children obtained from proposition 3.9. So we find this red vertex V such that some subset of it, X, of its children, the subtree rooted there, together has size between K over 2 and K. Okay, so let me call this blue blob, let's give it a name, let's call it B. Okay. Then we're almost done, right? By the, then we know that B, the size, is between K and K over 2. And furthermore, by observation, observation 3.1 implies that the neighborhood of G, of B in the graph G must lie in the subpath from their root. So it must be completely here. Their neighborhood must completely lie in the root V to the root of the whole tree up there. Okay. So let me call this guy P. Then we are done because we know its neighborhood goes only into this path P, right? You take the furthest neighbor. How many neighbors here? We know that this guy is of size at least T by our assumption of the graph expansion. Because B is of size between K and K over 2. So we have at least T vertices on this path P. Then you take the furthest one, you chase down this path. This is our cycle. Maybe I should use a different color, right? Okay, let me use another color. I'm running out of colors, purple. So you take the furthest path and you chase back. This is our cycle. That concludes the proof. Okay. So perfect. Exactly 10. Maybe I'll leave a couple minutes if you have questions about what we covered today. Tomorrow, I will move already to the second topic, which is on the Poch's rotation extension technique. That one is not as short as this one, so I'll do it in more details and slower. Okay, but any questions about today?
can I ask you a question? So for the longest path problem in random graph, is the constant log C over C best possible or anything like that?
Yeah, that's a very good question. So I make it into a series. So later on, we will see different methods improving on this result. So we will see a couple of improvement actually. I will give at least 3 different techniques, gives increasingly better and better bounds, eventually arriving to the best possible bound. Okay. Thanks for asking this question. Where is it? Here, 3.2. So the answer is no to your question. The best possible bound is in fact exponential in C, the error term. Here it's only polynomial 1 over C. You will see it's roughly C times e to the negative C, some exponential.
Thank you.
Any other questions? So yeah, maybe I was a little bit, I'm not sure if I was a little bit fast or not.
There is a question on the chatting.
So another question is the numbering related to something like a lecture notes? Yes, there will be a lecture note. So it's partly typed up. So after the whole series, I will share this PDF file.
And also I'm recording this lecture and I will, put it online and let you guys know where it is later.
Mm-hmm. Yeah, so, right. So tomorrow we will start the very famous Posha's rotation extension technique, and we will improve both of the 2 results we see today, the long path in the random graph and long cycle in expander graph. We will improve both of these. Okay, thanks for coming today.
Okay, yeah. Thank you for the good lecture. Yeah, see you guys tomorrow then.
Bye.
Okay, bye-bye.